So this is also about comet impact on the moon. And really on the second slide, you see the second slide, I show cold traps. The black contours are cold traps at 120 Kelvin, and some lunar prospect neutron data. And please right away that the amount of neutron suppression was on the amount of hydrogen is about the same in both hemispheres, but the cold traps are much larger in the south and in the north. And so the question is why, if water is just trapped in these cold traps, then there should be more in the south and the north, but there isn't. And also there is some correlation between the neutron suppression and the cold traps. It's not a very good correlation. So there is cold traps which appear to be have no neutron suppression. There is a cold trap which seems to have excessive neutron suppression. So what I'm exploring here is a scenario which, to see whether one can explain it, if all the water in this cold traps, or most of the water in this cold traps, comes from one single comet impact. So there's only one impact, and the basically location of this impact causes an unequal distribution in these cold traps. So that's what I'm exploring. And as has already come up here, of course, there is classical theory of water being transported in a exosphere by ballistic hops. And these ballistic hops of water molecules are very long. They're 200 kilometers. That's about 7 degrees in latitude. And so that's much bigger than the size of cold traps. So they easily hop from over the cold traps. So it's not clear whether an anisotropy in transport causes any heterogeneity in the ice deposition or not. There's also an issue whether molecules hop at all, but because of chemislection, but because the comet's impact are considered as so large, or really easily large enough to sort of wet the entire moon, so they really should hop along ballistic trajectories with thermal speed. And so we have simulated this with Monte Carlo method, which has been done several times before, including the previous speaker. But I don't simulate the comet impact directly, which was very nicely, which the previous speaker very nicely did, only with a Carlo Monte Carlo migration, and see what fraction of water gets trapped in the cold traps and where it gets cold trapped. And this usually has sort of association in flight, and the residence time is calculated from the surface temperature, which means they almost exclusively migrate on the daylight, and only partially, and mostly do not migrate on night side. Although there's a tiny bit of migration on night side too, where it's relatively warm. And so the next slide is a spread of. It's just an illustration of how it spreads. So there's two maps here of the moon. Each shows the entire moon. The red and yellow contours at the day side, the dark blue contours at the night side. And the impact is here assumed to be at 45 degree north latitude and at noon, and it's centered at noon. So half an hour after impact, all the black dots show molecules in flight. And 5 hours after impact, the image below, one sees the molecules are spread over the whole lunar disk, and the red ones are the ones that sit on the surface, and they sit potentially at the morning terminated, sort of because it's the coldest spots, and it's the sort of dusk dawn symmetry of a lot of molecules at the morning terminated. So just let that spread. And on the next slide, this is what happens after a day in this case. So these are cold traps, and all that's left is molecules sitting in the cold traps. And the larger the cold traps, the more molecules one expects in there. So the next slide, and this is so this is the basic first result. So I'm plotting here the fraction of water molecules trapped as a function of the latitude of impact. So if it impacts at the equator, then we have about 3 times as many water molecules trapped in the south than in the north, just because the cold trapping area is about 3 times larger. So, but if you have an impact at northern latitude, so 45 latitude, then the amount trapped in the northern and southern cold traps is about equal. So basically, most of the water in the cold traps comes from one impact, and this impact happening in mid-northern latitude, we would indeed expect the north and south to have about the same amount of water. And this amount is, by the way, about 1% of what's initially deposited, and which is smaller than previous calculations because now we think the area of the cold traps is an order of magnitude lower than is classically believed. So this number of 1% is lower only because the cold trap areas are lower, relying on temperature measure. Now, and that's pretty an obvious effect, of course, if you impact on the northern hemisphere, then you get a lot of water, more water in the north. Now, what's less clear is the longitudinal distribution. So, because the comet impacted a certain longitude, and because the day-night terminator is at a certain location at the time of impact, and most of the deposition happens within hours after impact, one can expect anisotropy in a transport. And so what I'm showing here is we again have an impact at nighttime here at 45 north, 45 latitude north, and then I'm seeing a ring-shaped cold trap just to figure out what the longitudinal dependence is. And the answer is a bit of longitude dependence to the north, with about a third difference between north and between dayside and night side, but not in the south because the south is further away, much further away from the impact in the north pole. And so the answer is there's only a small amount of longitudinal heterogeneity, and only in the hemisphere where the impact occurs. And that all makes sense, of course, because the hot length is so much larger than the cold traps. And so this is consistent with Newton data. Well, I think it only explains can only explain why there is more, there's as much water in the north than in the south. It does not explain, why some of these cold traps seem to be empty. It doesn't really explain the northern, the latitudinal asymmetry. But it does explain the amount. And so here is summarized again, this is a scenario I call a splash on the moon because it's a motion of impact, and one can figure out it's about, if one takes about 7 kilometer diameter impactor, then one gets sufficient water, half a meter or so, 1,000 cold traps. The transport is very asymmetric on north and day at night hemisphere with the position less so, but at mid-latitude, it ends up with about equal amount of water in the north and south. The crater rim is about 70 kilometers wide, and that all has to happen in the last billion years because the cold traps aren't older than that. So various impact areas over time. So it's a consistent scenario. So the conclusion is, well, the classical theory is ice is trapped in cold traps proportional to area. Problem is it doesn't quite correspond to neutron and other data. If most of this ice comes from a one-time impact of the comet at mid-northern latitude, it at least explains why there is so much water in the north compared to the south, where the area of the cold traps in the north is smaller. Longitudinal is only a small effect, and that's stronger I haven't really mentioned it, that's stronger for nighttime impact than for daytime impact. And as a last slide, let me just show a list of theories of ice storage on the moon. And so, the first is, of course, a classical cold trapping theory has been around for a long time, where water gradually accumulates in the cold traps. What I've talked about is the second line where you have a very asymmetric source, basically only one impact, which explains, might explain part of the pattern we see. And then the last line I'm just pointing out is the whole other mechanism called the ice pump, and I'm just finishing up a paper on that, where ice gets pumped into the subsurface, and it's not at the cold trap locations, but at other locations. And so, I don't think we have a satisfactory explanation yet why the ice is where it is. None of these, I think, is truly satisfactory.